Okay. On the test, the first set of questions is converting to scientific notation. Next set is sig figs, rounding to 3 sig figs. And then we did some operations. So let's go through. I'm going to do an example from each one. And if you want another example from each one, I'll do more. Okay. Okay, sig fig wise. I'm going to do these are the two that most people missed. Not a lot of people, but some people missed these. Okay, so how many sig figs does 90 have? 1. So our scientific notation number has to have 1 sig fig also. Okay, so 9 times 10 is 90. 7, how many sig figs is that? 1. We have to have a 10 to the exponent, and that's going to be 0. Because 10 to any number raised to the 0 power is equal to 1. That's an identity in math. The only exception is 0 to the 0 power is not 1. It's actually 1.5. Believe it or not. Yep. It's a very interesting conundrum. I just put it as undefined, but there is quite a few examples. If you go online, what is 0 to the 0 power equal? Actually, it's not 1. Look up some of them. I mean, you've got a background in limits. Look it up. It's very interesting. And I didn't buy it, but all right. So you want me to do any more examples on converting to scientific notation? I'll do one more. Okay, so how many sig figs is that? 3. Beginning zeros never count. Zeros in the middle always count. Zeros at the end count if there's a decimal place, and there is a decimal place there. So, but we know how many zeros at the end. Okay, so we're going to write it counts. Yeah. All right. So we need our new scientific notation number has to have 3 sig figs. All right, now let me show you a shortcut if there's a number that's less than 1. Count the zeros, and if it doesn't have a 0 point, add 1. Okay, so if we had, okay, so count the zeros. That's 5, right? If there's no 0 in front, count the zeros, add 1. I know a lot of you, I saw in the test, you were going like this, which is fine, except this kind of a shortcut works pretty well. All right, sig figs. Oops. Okay, sig figs on this one. We've got zeros in the middle that count, zeros at the end. And is there a decimal point there? No decimal point. So count the middle because they always count. Ones in the beginning never count, and there's none there. The ones at the end only count if there's a decimal point. No decimal point, so it doesn't count. So that means it's 5. A fair number of you put 6 down. That's 5. And we're going to understand why that last 0 doesn't count. If we had that would be 6 then, because there is a decimal point present. Yeah. This 5. Did you get it right? If you have an error and it's to your favor, make sure you talk to me. If I didn't mark it wrong and it's wrong, it's a gift. Okay? No, seriously, but that was my fault. So it's a gift. And I graded these really fast. I wanted to get them back to you. And there were 50 of them to grade. And all right, let's do one more of these. Okay, so we have a decimal point, and we have a trailing 0, so that 0 counts. We have, and the ones in the beginning don't count. So that's 3. Yeah. Oh, yeah. Okay. Now this is one that I want to go over, is rounding to 3 sig figs. Now, whenever we have a number, let me write this guy here. First of all, is that proper scientific notation? Okay, so let's look at that number. The first number has to be a number from 1 to 9.999. Is that number from 1 to 9.9? No. So automatically it's not proper scientific notation. So your final answer after you round it to 3 sig figs is going to have to be in proper scientific notation. Now, I did not mark off if you didn't put it in proper scientific notation because I didn't tell you that. But normally, if you have a number with an exponent in it like that, always put it in proper scientific notation. So proper scientific notation would be what would it be? Okay, we're gonna divide that by 100. So we have to multiply this by 100. Yeah, because 100 is 10 to the squared, positive squared. So -8 plus 2 is -6. All right, so 3 sig figs. So we go to the 4th place. That's 4 or 0. So we just drop everything. So the answer is 381 times 10 to the -6. If you put 381 times 10 to the -8, I gave you credit for it. But this would be the proper, the lower one would be the proper scientific notation. Okay, 1,000. And notice there's a decimal point there. So how many sig figs is that number? 4 sig figs. We want to go to 3 sig figs. So what do you think the best way to do that is? Scientific notation is our friend in this case. So we're going to move it over to scientific notation. And yes, you're right. Okay, and that would be three places. Yeah, a number of people missed this one and the one below it, or the one above it. Does this make sense? You mean like this? How many sig figs is 100? Now, if you put it like this, now we have a decimal point, so all of them would count. Yes, this is by far preferred though over that. Yeah, so I gave people credit for if you did it this way, because I didn't say put it in proper scientific notation, which yeah, so this is going to be the practice test for my fall class. Okay, all right. Now the next one, you guys did pretty well on this one where you're doing some operations. I'm going to do, which is now when you put this in your calculator, you don't need to have the parentheses. You can if you want. It's just extra keystrokes, but they're not needed. Well, I've got the answer here. Okay, so this is going to be okay. So 5 sig figs, 5 sig figs, 5 sig figs. So whether you, the way you put this in your calculator, you're going to go you're going to go 1.3234 EE change sign 4 times 17.332 enter. No parentheses. If you put the parentheses in, it would be fine, but that's 4 extra keystrokes. And you get the same answer. On the third one, part C, there are 2 answers. Because a lot of you interpreted this, the slash as a multiplication sign, not a division. So this one, the way you do it is 5.55 times EE, excuse me, back up. 5.55 EE 4, divide key. So this is 503.455 EE, change sign, 12, enter. Now, those of you who didn't recognize this as division and you did it as a multiplication problem, I gave you credit. So if you had 2.79 times 10 to the minus fifth as an answer, I accepted that. Now, some of the early tests I was grading, I think I marked that wrong. And if you were in that group, you might have got dinged on it. So I'll give you those points though, okay? All right. Next one's on performing conversions. This was kind of a hit and miss with you guys. Let's do, we'll do the last one. Now, NG stands for nanograms. Nanograms is a billionth of a gram. So the first step is to get to grams. We're in grams now. So the trick, this is the part where if you miss this problem, this is where you missed it. Okay, a lot of you put this down as an answer. What is wrong with that conversion factor? Huh? They were doing 5C. Right. I already got rid of the kilograms. Now we're in grams. And the grams will cancel. The problem is the numbers are not correct. Yeah. Huh? Yes. Should be positive 9. Because let me tell you why. A nanogram is really, really, really tiny. A gram is huge compared to a nanogram. And remember, with a conversion factor, the top and bottom have to be equal. So we're saying a billionth of a gram. That's 10 to the 9th times 10 to the 9th equals a whole gram? No. But a billion nanograms is equal to 1 gram. Okay, so conversion factors, they won't work unless the top and bottom, the numerator and denominator, are equal. It's extremely important to make sure they're equal. Okay? And then now it makes sense. Remember I said, analyze your answer. So if we're going to kilograms, which is big, and going to nanograms, we have to have a whole bunch of nanograms to equal a 24 kilograms. And our answer is that 10 to the 13th. That's a gigantic number. So your answer makes sense. Some of you had minus exponents. Oh, yeah, that's right. That's the same thing.
Okay.
So you have a billionth of a gram is equal to 1 nanogram. Yeah. Yeah, so there are 2 of these conversions you could use. Okay, the other conversion factor, which she used, is instead of 10 to the plus 9 nanograms, she used 1 nanogram over 10 to the minus ninth grams. And you get the same exact answer. Yeah. Oh, I dinged you on your setup. Remember the setup, you have to have your units canceling. And you also did a shortcut. Instead of 2 conversions, you did it all in 1. And you can do that, that's fine, except it's easier to make an error that way. I still gave you 4 out of 8. All right, does this make sense, this problem? Of all the conversions, this one was missed the most. All right. Is it hot in here? I'm not doing very well. Oh, seriously, I'm not doing very well right now. Okay, on the next one, next page, we had 3 problems. Speed limit, heartbeats per, not breaths per year, but beats per year. And then the last one, more people missed that one. So I'm going to go over that one first. And MI is for miles, not M. What does M stand for? Lowercase m. Meters. Some of you put M down. MI is miles. Okay, and we want to end up with square meters. Now, if you're starting and ending with something squared or cubed, the conversion factors have to reflect that cubed or squareness. And I didn't give you a conversion factor for squared meters or cubic meters or whatever. So you need to do that conversion of the conversion factor. Okay, I gave you 1.609 kilometers per mile. And we need it per square mile. So if I square that, I'm going to also square that. So this gets us to square kilometers. Now we're going to go from square kilometers to square meters. And there are 1,000 meters in a kilometer. But it also has to be squared. Now, if this was cubic, we'd have to do cubes all the way through. Now, one error that a lot of you did, if you missed this problem, I gave you partial credit, but if you missed this one, the way you worked it, some of you went 1.97 times 1.609 EE2. It's not the same thing as 1.609 squared. So depending on your calculator, Some of you had an X squared button to push. You'd push that instead of caret 2. So you go 1.97 times 1.609 caret. I don't know how they got the word caret out of that. 2 times 1000 caret 2, enter. And some of the TI calculators have got an X squared. So you, instead of saying caret 2, you just hit the X squared. Button in lieu of the caret 2. Okay, a lot of you didn't square the 1.6 with 1000. Okay, I want to go over the heartbeat because that's so if you're given is a single number, that means your answer has to be a single number. Okay, if you start with a fraction, your answer is going to be a fraction. So the problem above that, person's heartbeat average of once every 63 beats per minute. Okay, that's what's given, and that's a fraction. So for given is a fraction, your answer has to be a fraction. So the answer we want is beats per year. Now, the numerator is already in beats, so we don't have to do anything with the numerator we're starting with. We have to deal with the minutes. So we're going to get minutes to years. So that's what the conversions are going to be doing. An hour. Again, that gets us to minutes. Now we get to hours. Oops, days. Sorry. Okay, now we're in days, and then now we're going to go to per year. So what's left over? Beats per year. That's what we want. But the main thing is if you start with a fraction, you got to end with a fraction. If you start with just a single number, you're going to end with a single number. Okay, and then lastly, for those who did the take-home problem, okay, there's a couple ways to approach this. We need to figure out how many gallons of all the people in the world, not excuse me, all the people in the United States in year 2011, whatever it was, how many gallons did that consume? So firstly, you can do how many gallons does one car consume in a year? Yeah, and then you're going to multiply that by the number of cars in the United States, but not everyone in the United States owned one car. So you had to do a conversion. It's one car per family. And it's 3.16? 3.16 people made up a family. And then you multiply that by the gallons in one car. All right, so this is what it looks like. So first we're going to calculate gallons for one car. And we use one tank a week. Now we know how many gallons we used in a week. Okay, so that this gives us gallons for one car. Just doing a straight burner in a tank a week, 15 gallons in a tank. We got 52 weeks per year. That gives us gallons for one car. Now we need to figure out how many cars there are in the United States in 2011. Okay, so what we're going to do now is we're going to continue with that setup. Now you can also just substitute in and now we need to take and find out how many cars there are in the United States. Okay, so we have one car per family. Okay, so what do we have left over here? We have cars per year. Now, some of you took that number and substituted it for that, which is fine. Just did it in 2 steps. Or you can do it all together. Hmm? But you have to, when we do it all together, still, it's still built into that altogether. You got credit for it, all right? Okay. All right. So, so if I owe you points, or if you think I owe you points, I have no problem for you to defend your answer. If your answer is reasonable, I can give you points for it. If it's not reasonable, well, you know, you tried. Okay, any more questions about the test? Again, I'll remind you, if your final score is higher than this test, I'm going to swap it out. This test will go away. Now, questions on the final, though, include questions like this, though. Okay. Yes. The advantage of taking me for multiple semesters is I have the old tests as examples. All right, so let's go ahead on. Now, there's a simple relationship. Let me review temperature. Temperature is the metric we use to measure the kinetic energy in an atom or molecule. Higher the temperature, the more kinetic energy, and kinetic energy is the energy of motion. So the higher the temperature, the more the atom or molecule is moving. You guys. Okay, so again, kinetic energy is the energy or metric used to dictate the degree of motion of an atom or molecule. Yeah.
What's the difference between thermal and kinetic energy?
Actually, nothing. Because thermal energy is energy of heat. To get heat, you have to have molecules beating against something, which is motion. So,
yeah.
All right. His question was, what's the difference between thermal and kinetic energy? None. Okay, so when we take and have no movement whatsoever, that would be 0 if we're using the right scale. And that right scale is called Kelvin, K. So Celsius is 273.15 degrees higher than the Kelvin scale. So if I give you something in Kelvin to convert it, you just add 273.15. I give you something in Celsius, convert to Kelvin, you subtract 273. So the magic number here is 273.15. And it's a simple, it's not even an algebraic relationship. It's just a simple difference between the two. Now, there is a relationship between Fahrenheit and Celsius. And there's some conversion factors and all that junk. We're in a science class, we use metric units. So I'm never going to ask you to go from Fahrenheit to centigrade. But you do need to know that Fahrenheit is also a metric. The units are different with Fahrenheit versus Celsius. but the concept is exactly the same. So that means at absolute zero for Fahrenheit, there's a scale called Rankine, R-A-N-K-N-E. Engineers used to use that a lot. They don't use that much anymore. So again, so temperature generically is a measurement of kinetic energy and motion of the molecules.
How cold is space?
Varies a lot. Depends on what,
Outside of-
depends how close you are to something hot. Like how close are you to the sun? Like Mercury is really close to the sun. So when you're standing on Mercury, you wouldn't last very long. Probably nanoseconds. Because there's nothing to interrupt the temperature other than distance. And it's a squared relationship. So you have to go out twice as far to be double, or 8 times out to be triple, you know, so it's this. Okay, so just as a reference now, if water boils at water boils at 100 degrees Celsius, and what does it boil at Kelvin wise? All we need to do is add just add 273.15. No, it's by definition 100. Good question. Okay, now why do we need to worry about Kelvin? When we get into thermodynamics and gas laws, they use Kelvin. If you're not doing thermodynamics, you don't have to worry about it. If you're not doing a gas law equation, you don't have to worry about it. Now, we're not going to do much of either one of those here. We're going to do a little bit on gases. We're going to have a simulation for gases. We'll be doing it at home, but it's not a lot. Now, 1A has a ton on gases, a ton. It's called the kinetic theory of gases, and there's a whole bunch of calculations. And well, they'll teach it to you, so you will learn it. You don't have to learn it now. Okay, so that's the main thing about temperature. Oh, and then just remember another conversion factor, 273.15 difference between Celsius, or some people call it Celsius, some people call it centigrade. I like centigrade better than Celsius, but because it connotes there's 100 degrees between the two references, but a lot of times I'll use Celsius. Same thing though. Okay, that's what I wanted to cover today. And we have 20 minutes before lab. So what I'd like to tell you to do is those of you who haven't written up your pre-lab yet and have lab today, that'll give you time to do that. Okay, yeah. Yes. Yeah, the lab today is going to be fun. We're going to be using the Bunsen burner and Yes and no, because you can't go to 2B without taking 2A. But they'll eventually kick you out though. Because the computer will look at your prereqs. So you'll do really well in 2A with taking this class. I mean, really well. You'll find a lot of overlap, probably 80% overlap. That's a killer in summer. And you have 4 labs a week. Right. No, I'm not exaggerating. It's a killer. Well, you cover 16-week material in 8 weeks. Yeah. Yeah. It's going to be analogously rough. Excuse me, let me terminate this recording.